Hello, welcome to another lecture for physics. Today we're going to be covering the concept of work and what work is in relation to the general ideas behind physics. So let's start off with a little thought process here. We have a particle here, something, and we want to move it to here. Intuitively, if you have some object here and some object here, and you want to get it to that point, you obviously have to apply a force, and it's going to go some small little distances as it continues to go on some path as you're pushing it to get to that location. So, doing all of this, the general idea behind work and what work, I guess, is defined as is how much energy it takes to move a particle from one place to another. That is essentially what work is and how you can go about using it. So, let's say you wanted to move that again. The way we can derive this formula is we know that there's some force acted along some kind of distance. So we have this little force, and it's going across some distance dx, and we have an infinite number of these forces going to some dx. The energy behind this can be defined as the integral from position A to position B of all the force vectors dotted with the dx vectors. This is your work equation. So once you evaluate that integral, you're going to end up with force times distance times cosine theta. And the reason why you have that cosine theta is because when you do a vector dot product, as such, f vector dotted with a dx vector, the dot product returns a scalar value, so you won't get a vector out of this. You'll get a scalar value. And the cosine attached to it is determined by the angle between the two vectors. So, for instance, if you have a force vector pointing this way, but your direction of motion, your distance is this way, the difference between the two vectors, the angle difference between them, will be your cosine theta. Well, that'll be your theta right there. So let's do an example. We have this guy, he's pushing this lawnmower at some angle theta, and it is going some distance d. How much work does the man do to move the machine after a distance d? So, he's going a distance d, but he's pushing on this lawnmower with some force at some angle. So, based off our equation, we have the integral from 0 to d, right, because that's the total distance, of the force dotted with the dx vector. That'll give us our work. The force here that will do work on this is only the force in that direction. The force in this direction is cosine of 90, which is going to be 0. So, you would just have to do force times the distance times that cosine angle that's in there, and that it gives you your work. It would be f cosine theta times that distance, and that's your work. Let's do another example. So let's say you have a block, and it's some height h above the ground. It has some coefficient of friction. How much work is done on the block by friction as it slides down the surface? So let's assume that, well, we know the direction of motion is that way, and all we're looking for is the work that this block is, that the friction is doing on this block. So let's draw a Fibonacci diagram of our block. We have gravity going down. We have the normal force going at the angle. We have our friction force pointing backwards, and that's it. And if we split this up doing that trick of eighths, we know the angle will end up right there. So, if we sum our forces in the x direction, we have mg, this would be mg cosine theta since we're going to define our axis as being positive x going down. So we'll say xy. Mg cosine theta minus the force of friction is equal to ma. And sums of forces in the y direction, we'll have mg sine theta negative. So we'll just say this will be the normal force minus mg sine theta is equal to 0, because it's not going to be accelerating into the block. So we can say the normal force is equal to mg sine theta. So we know the normal force now, and we know the magnitude of that. Let's go back to our work equation where we said it's the integral from position 1, which would be here, to position 2 of the force dotted with the distance. And this gives us our work. We have to talk about what the friction force is, right? Because that's the force that we're looking for. So the force of friction is, this is sliding, so it's going to have the coefficient of kinetic friction times the normal force. So the friction force is going to equal to mu k times mg sine of theta. So we can plug that into our equation here. So we have mu k mg sine theta dotted with our dx vector. Or what we can do is we'll leave that to the end, and we'll plug that in after we integrate. So the next thing we need to know is this dx vector and how far this distance is once it gets to the bottom of the hill. We have some angle, we have some height, so based off that, we know that we're looking for the hypotenuse, and we have the opposite. So we're looking for the opposite over the hypotenuse. That is, we have the opposite, we're looking for the hypotenuse. So that's right? Opposite over hypotenuse. So this is sine of theta. We have that theta, we have the opposite, we're looking for the height, so we would have height divided by the sine of theta, and that would give us our hypotenuse. And that's the distance that it travels, which equals d. So integrating this from 0 to d, we have f d cosine of the angle between them is equal, so we'll go ahead and actually just write out this portion here. So we have f d cosine of the angle between them is equal to the work done by these two. Since the direction of motion is this way, and the distance vector is, or the direction of motion and the distance vector are the same thing, and they're going in that direction, and the work is going in that direction, we're going to have some negative work done by this friction. So, right, because the dot product tells us when you dot it, you get this FD cosine theta, and this theta here is the angle between the two vectors. This here is the friction vector. This here is the vector, the distance vector, the displacement vector, the direction vector, the velocity vector, the direction of movement vector, essentially. The angle between these two is 180 degrees. Cosine of 180 degrees is equal to -1. Degrees is equal to -1. So we're going to have negative FD is equal to the work. We know again that the force is going to be just negative. So we said it's mu k mg sine of theta. We said it's negative, right, because the work done is negative. We know the distance, and this is equal to work. So we said the distance is h over sine theta. So we have negative mu k mg sine theta times the distance, which is going to be h, which is going to be, mini h, divided by sine theta. That equals our work. Our sine thetas will cancel, and we'll have negative mu k mg times h is equal to the work done. So thank you for coming to this lecture, and in the next one we'll talk about energy.